is just ASCII, very handy for printf, and also half of the in-jokes in Futurama is in ASCII. So really the only thing to worry about is make sure your TX goes to their RX. And have their
The
TX.
mistake is connecting the TXs together. Because both of the chips, when they say their TX line, is that's the line that they are trying to set to send data. And so if you connect them together, both of them are just going to try and wiggle this line, and both of them are going to look at the other line that no one's talking
And
about.
the way this used to work in the good old days is you'd actually have a null modem. You'd have your serial cable, and then you'd have a little dongle that's called a null modem, which basically just, all it did is it swapped the TX and RX lines so you could plug them in. And that's how you had to do multiplayer video games back in the early 90s.
Yeah, early 90s.
Anyway, it worked. And
I ran one all the way to
does
the
anyone
next
actually
neighbor's
possess
house
the null
once.
modem? Yeah, I think so.
Yeah.
You're not missing anything. These are wonderful things to get rid of. But on microcontrollers, right, on a 25-cent chip, you can now do what like state-of-the-art, computers did, 20 years ago. And it's like, okay.
Yeah, the second most common issue is that you're actually talking on the wrong baud rate because you didn't read the data sheet or you forgot to set your settings correctly or some reason that you have.
And there's two possibilities. One is you just read the wrong thing. A lot of devices are configurable, and you might configure it to some faster speed and then forget you did that. And you're trying to factor in default settings.
And the second is that you have miscalculated how to set your baud rate because they don't nicely say like, I would like to set this to 115/200. They're like, how should I divide my clock? Basically, that's the setting you actually set. And so that depends on, are you running a 20 megahertz microcontroller or a 9 megahertz microcontroller? There's a little formula that you
There's
have
a
to solve.
formula, and for 18 megas and 18 tinies, they're a little kind you would just say, here's this giant table. What frequency you're running at, set it to this bit. And like, you don't have to worry. Because there's a little detail with the formula, which is, you do the formula, and then you might be dead on if you're doing something that's a fractional, because all these things are based on that weird 115/200, which is 1/16 of 3.4864, that crazy crystal I can never
That no
remember.
one has anymore.
No one uses them. Now people run at 8 megahertz, 16 megahertz, 200 megahertz. Nobody runs
Yeah,
it.
so you're never exactly on with your formula, and sometimes there are multiple ways of solving it that gets you closer or further. So the long and short of it is, usually you just want to try and find these settings online somewhere or in a data sheet. But it is very common to get them set wrong, even if you know what you're doing, just because it's a lot of fiddly.
And you use the formula, you think you're clever, and then you end up being off by -3%. And it turns out that the other chip you're talking to got the formula off by +2%. So now you're off by 5% and it doesn't work. And you have to get it wrong in the right direction.
That is
XDs
less common these days.
XDs do that.
Okay, but it's less common in general.
Okay, so that's serial. But now we're going to talk about the serial peripheral interface. So what is this? Everything's serial.
So basically the idea is that Serial came out of the need for two devices that are basically like running their own microcontrollers to talk to each other. Because they have their own clocks, they're doing their own thing, they want to communicate data to them. So it's asynchronous, and it's usually at these high voltage levels, so you can run it on a long cable. So now chip manufacturers are like, well, we want to run stuff too, but if I have a tiny little device, I don't want to have to like put a crystal in it that has to run and then run this asynchronous protocol. So a couple of new protocols spun out that basically don't require one of the chips to have its own clock. And these are synchronous serial interfaces. And one of them is SPI. So SPI is what's typically used for when you have a bunch of smaller dependent devices that are connecting to something like a microcontroller. So it's a lot simpler in terms of the implementation, but it uses more lines, and it's more designed for if you have two things on the same board really close to each other, and you want to talk between them really, really fast, and one of the devices is really simple.
Yeah, and the idea here is that one of the devices is basically always in charge. So they have computer technology, they love master-slave terminology. That's basically what it is. Somebody's in charge, and the other people are not in charge. And whoever's in charge is in charge of either doing slave select, it's also called chip select. And what they do is you say, hey, I'm talking to you, and then you actually provide the clock. So they just have And what this, if you're familiar with registers, what this literally is you have a register filled with data, and then the master gives you a clock, and you clock it out as a shift register. That's all it is you're shifting the data bits out, and the data comes out
At the same speed as this clock.
Yeah.
So basically, you're saying, okay, you device, give me your data, and you wiggle the clock line, and it just says, oh, I'm getting clocked here, have this data. And then basically, you can also send data. You can wiggle your clock and also wiggle out a data line, and the slave basically
And the
gets
nice
that
thing
into
is
its
that
register.
there's no confusion. The clock line is the same on both chips. The MOSI line is the same on both chips. The MISO line is the same on both
Because
chips.
both of them agree which side is the master and which side is the slave. And so you don't have to do any weird flipping of these lines. You don't have to do any weird clocking, or you just have to sort of get it within a range of whatever the device supports, which is usually really, really, really large. And so it's really nice for on board where you don't have to worry about these things.
Yeah.
And it's really easy for manufacturers because they don't have to make a device that
Shift
runs as a
registers
clock.
turn out to be really easy to design and implement and get right and describe. So that's why everyone likes it. And what's really nice about it is, you say, well, that's a lot of lines to be using. What happens if I want to have 10 sensors that I need to read over SPI? I don't want to have 50 lines. Well, you don't actually have to. You just have to have these three, and then most devices that support SPI agree that when the chip select line is floating high, they do not touch anything. They don't do anything when the other lines are going. So they disable their outputs. And so what that means is if you have 10 sensors, you just have 10 different chip select lines, and you only talk to one at a time. And you get to pick which one. It's not hodgepodge of insanity. And you can clock at whatever speed you want. And you just make sure it's either not too fast for your device, but in reality, nowadays, your microcontroller is going to be the slowest thing on the SPI bus. So it's great because you don't have to figure out the baud rate. There's no clock skew unless you're on like 10-foot wires. They go super fast. Your things can go 8 megahertz. So like if you're talking to like a memory chip and you want to store a whole bunch of memory, that memory chip can go faster than you possibly could. And what's really interesting is that you can actually, if you're manually clocking it, you can just pause halfway, do something else for a while, and then continue clocking it later. Nothing happens. It generally just works. Now the detail is that you have to know about the data format.
So unlike the previous computer serial, this spec really only defines those lines. It doesn't really define how data is passed along those lines. And so different manufacturers have different ideas as to whether a high means a 1 or a 0. They have different ideas as to sort of how long the register blocks are, although they're usually 8 bits. They have different ideas as to if you're sending something that's 4 bytes as to whether the most significant or least significant byte. Right, that's true. So basically, you have to figure out what the person on the other end is actually going to send you in terms of the actual byte or bits that you receive.
You don't necessarily have to understand what's going on here, but in the data sheet, it tells you this is what we do, and then you make the Atmel chip match what it's doing.
Yes, once again, the Atmel chips are very nice, and most microcontrollers are, in that they have settings to deal with all of this. They can automatically flip the bits. They can automatically read in different block sizes in hardware. You just have to tell them what you want them to do. And so, once again, registers, you set them, and then everything will just sort of go.
And you do have to make sure your voltages are compatible or tolerant. There's no RS-232 for SPI, but what you'll frequently have is your microcontroller, if it's running at 5 volts, you do not want to talk to a 3-volt SPI chip because you will blow up its...
Unless it says it's tolerant.
It may say 5-volt tolerant.
Yeah.
And you may find that like a lot of very cool chips, like tiny accelerometers that cost $1 and do everything, make you breakfast, they're 1.8 volt devices, but they're 3.3 volt tolerant. So then you say, well, should I be using 5 volts on my microcontroller? The answer is no, not without additional circuitry to interface. So that's just, you keep that in mind for when you pick what your VCC should be.
Okay, so here's an example of what's going on all of these lines when we're doing an SPI transfer of data. So one thing that's kind of interesting is that really you can actually have data going both ways on the same select and clock cycle, but of course, usually you have to specify something ahead
So
of
what
time.
this is, just to give you the high level, for most SPI devices, the most common way to interface to them is first you select them, then you give them some sort of command and maybe some data, and then what you do is you just start clocking out zeros.
Whatever, yeah.
It no longer matters, you're just running the clock, and then they answer your command. So
All
one
the
common
same.
example might be temperature, crazy sensor, give me your temperature. And then, once you've told it that, the next thing it does is it gives you its temperature.
And you're actually providing these 3 lines. You're doing the chip select, and you're actually running the clock. Even when that guy's sending to you, you're providing him the clock that he's using to send you bytes. And so you have to make sure that you're actually doing that long enough for him to send all the bytes that you're interested in.
But it's actually very simple. You set this pin below. So in your code, what it ends up looking like is start transaction. Data byte 0 is blocked. Wait, byte 1 is blocked. Byte 3. And then you just keep reading until you have all the data you want. And when you're done, you just set the pin high again. And you're done with that chip. And then you go on to the next chip or the next chip. And you generally set it high. Even if the next thing you want to do is talk to this chip, you frequently set this high again because that resets the little state machine. So basically, a little organ grinder, little pop goes the weasel sort of thing, where you just turn the cranks to get the data you want, you reset the thing, and then you do it all over again. So when you start getting into the awful details,
Yeah, so here's where you
we'll
have to
talk
sort of
about
match stuff up.
briefly,
Well, we can
but
talk about it in
basically-
more detail, yeah. Basically, you can either sample on the leading edges of clocks or the falling edges of clocks, and you can either sample things with inverted logic or uninverted logic, and different manufacturers will say basically we set our bits out, we set the value of them on the falling edge of the clock. And so you say, well, I'll read on the rising edge, which would be right in the middle of a bit where it's really stable. And you'll see lots of diagrams like this in the data sheet that sort of tell you, okay, on the falling edge of the clock, that's right in the middle of where this data bit is set. So that's what I want. And they'll tell you, whether they are inverting their logic on the lines.
So it's a little kind of awful to look at, and in general, kind of beyond the scope of what we want you to do in this class. But just be aware this exists. In reality, when you're actually writing this code, there are 4 modes. There's mode 0, mode 1, mode 2, and mode 3. Usually, everyone uses mode 0 or mode 3. You try one or the other. If that doesn't work, try mode 1 or try mode 2. One of them is going to start giving you the right data.
Yep. Thankfully, you don't have a million baud rate configurations or clock dividers or anything. You just have to work out these
We'll give you a hand if you're having trouble with this, but generally, you just have to figure out which one it is. Your code will start reading it, and then you're good to go.
And other than getting gibberish, there's no real harm in trying the wrong mode.
Yeah.
It just reads gibberish or writes gibberish.
But basically, at some point, you get to where you can look at these super thrilling things and say, aha, I should be doing this. And we'll help you along with that if you need to use beyond these gadgets. And if you're lucky, someone will just say, oh, somewhere in the data sheet, like, hey, we use little endian and we're mode 3. And you say, great, now I just have to type that in and it works. Okay, so the last super thrilling
Serial
interface that everybody uses, especially for these small embedded things that you guys are building, is I2C, which is the Inter-Integrated Circuit Bus.
So I think this was Texas Instruments?
Philips?
Philips? Okay, Philips. Philips was like, we want a bus that's a serial protocol that we can put multiple devices on and not have to use a bunch of different clock select lines. They can all share the same transmit and receive lines. So they made a slightly more complicated protocol so they wouldn't have to run all these extra select
And
lines.
very important, this is a bus. And what that means is you can basically have multiple masters. Other people can be in charge. It's not just somebody's in charge, everybody else does whatever he tells it to. There can be multiple things in charge querying the same thing. And so what that means is there has to be arbitration, there has to be addressability, all kinds of shenanigans. Now, you'll never find the word I2C in your Atmel data sheets, and that's because that's trademarked. You have to pay a license. However, many people often implement two-wire serial or TWI, because they have very identical formats, but it's not licensed.
So you can see here that there's just these 3 lines, and you can put 10 devices, and they all share these 3 lines, and that's what that extra complexity is letting you do.
Now for I2C, this is becoming less true over time, but there's a few fixed speeds that are defined in hardware. You either support low speed or high speed, and I think now there's super high speed, just to keep things complicated. The data format and the arbitration are hardware defined. You don't have a choice. What happens is this is an open drain system, and basically what that means is everybody can pull something low, but when they let go, it floats back up to some other, to the voltage.
And they have no mechanism for driving anything high.
And the reason for that is, let's say you have 2 things that are fighting with each other. If you hook up 2 transmit lines of microcontrollers to each other, you can do bad things where one of them is overpowering the other, and the other one is forced to accept current, and you may blow the thing up. And that's bad. So the way they work around that is they make sure that everybody can only sync current. And that way, when 2 people try to take control of the bus and sync current at the same time, nothing bad happens to the chips. And then there's details where, and so what happens is there's pull-up resistors to make it work. And it's kind of flimsy. I2C is my least favorite of the protocols because it's kind of flimsy. It's meant for a PCB. You have to if you have problems, you have to change the resistance values. If you're trying to run long wires to some sensor that talks I2C, you can have problems with wires that are just too long and you've got to do something funny.
Yeah, because it's open drain, setting this resistor or set of resistors that pull everything up is really important, because if it's too high of a resistance, then essentially when you drain it, it'll take a while to float back up, and that can cause problems. And if it's too big, then you might have problems draining it in the first place over a really long wire length.
And then usually what's nice is that they're all open drain. Usually compatible voltages, they're almost always 5 volt tolerant, even if they're 1.8 volt devices, just because it's super easy to do that.
Yep. Since all they're doing is syncing current, they just have a little switch. They don't really care what the voltage of the bus is.
And what's really nice about it is these can be very small devices. They only need 4 lines: power, ground, and then these 2 data lines. So you end up with very small devices, and it's just, you want to use them on a PCB. If you're running 6-foot wires to them, you may have problems.
Oh, that got washed out of it.
Yeah. Well, anyway, here's microcontroller, and here's 3 random devices.
Yep, and they're all sharing the same 2 transmit receive lines, and you can see the pull-up resistors here, which are shared for all of them.
Yeah. And you can have 100 things on here. So if you're really cramped for space, you're like, man, I really want to have all these crazy sensors, but I only have a small chip with not a lot of pins because I have a small board. Here you go. This is how you can have a million things at the board. And then I don't want to get too much into the I2C specification, but basically, like SPI, you want to be able to write commands and then also read data. And the way they do that is, of these 8 bits, one of them is special. The bottom bit is special, and it either means I'm sending you a write command or I'm sending you a read command. So it's another way where they do very simple bidirectional kind of stuff. And that's why there's only, technically there should be 127 unique addresses, but there's a couple for I2C extended mode, so that goes away. But I don't want to get into that. But anyway, you can have a lot. And then, let's see, we got a couple magic states. And then there's arbitration. There's almost always hardware arbitration. You only run into this if you're trying to implement I2C in software. And then you have to implement all these features. But all of your ML chips generally have I2C.
Yep, as TWI.
Yeah. So let's...
and a lot of the time, you don't have to worry about this, because in most of the circuits that you're doing, your microcontroller is always going to be the single master on the bus. And all of the other devices are going to be not masters. So it's usually fine to just use some of the more common master modes available in TWI. You don't have to do crazy multi-master stuff most of the time.
Yeah, don't do it. One nice thing about I2C is when you send a bits of data to your other device, they actually will do a pulse on the 9th bit and just see what happens. And then you can actually know whether someone's actually listening to you. Whereas SPI, you can clock in for days and you never know if you get zeros because the other device is saying 0, or if it's dead, someone forgot to solder it in. You don't know. Whereas I2C, you send them a command or some request, and if they don't respond to you, you know they didn't respond to you. So it's kind of a nice sort of positive response. Then there's some clock scratching. If you're implementing your own I2C slave, you could break the whole I2C bus. Usually people who sell things don't. So being an I2C master is very easy on that chip. I don't recommend being an I2C slave though. So in terms of what actually happens, it's not too bad. The master waits for the bus to be idle, and if you're the only master, it's pretty easy. And then what you do is you start a command, then you write an address, you would maybe write a command like, hey, give me your temperature, and then you would issue a restart, write to the same address with a read, and then read a data byte. And then in theory, you just got the temperature byte. Or if it's 2 bytes, you'd read 2 bytes in a row. And then you would do an I2C stop. And that lets go of the bus and resets the transaction.
And you can see that what's going on here is very similar to what's going on in SPI, except that both the master and slave are sharing the same bus for data signaling. And they just have this protocol in place for them not to be writing at the same time.
And so if you look, it's a little bit more work than the SPI example where you're just like, I'm going to start this transaction, here's the commands I want, and now I'm just going to keep reading, and the data bytes I want are going to come back. Whereas here you have to write some commands, restart the bus, read the stuff. So it's a little bit more work. And that's the most common way it's used. You can eventually, what you often do is you set up the I2C device with some write commands, and then every time you read from it, it gives you the data you want. Just to simplify this, because this is kind of a little bit of work. The code ends up being pretty short, but it's a little tedious. So yeah, APR master code is pretty easy. We're going to talk about that next week. In terms of devices, most have a single hard-coded address. So if you want to buy a temperature sensor from DigiKey, you can get these super tiny things with like 3 or 4 pins, but they only have one address. And they'll say, my address is number 37. And that's great until you want to say, well, gee, what if I want the temperature over here and over here? They both have address 37. You can't use that chip. Or you get unlucky and somebody else's accelerometer also uses 37, which is super annoying. So what frequently happens is you have these chips where it really could be a 4-pin chip, but they end up having 8 or 16 pins just so that you can set some high, low set pins just so it's got a different address.
Yeah.
So it'll say, I'm going to be 37 plus some offset based on whatever you set on these little dip switches. And you're good to go. And so sometimes like temperature sensors will be like, oh, this temperature sensor can have 8 unique values. This one can have 16 unique values. And that's how you pick which one you want based on how many you're going to use. And in general, really what you do is you see if it works. Just put it on your board and see if it works. But sometimes you might have to see what you're actually looking for is when you turn off your 0, you want to go back to 1 real fast. But if your pull-up resistor is too high for some reason, you're going to have this sort of gentle return to 1, and that's not going to work. And you just lower your resistance. It's as simple as that. But nowadays, things are a lot better about that. And it actually gives lower and lower values. Okay, so that's sort of the fun with the 3 big serial interfaces.
So those are the protocols that you will actually probably use on most microcontrollers. There are newer ones that directly support more advanced protocols, but those protocols tend to be more complicated. And some of them are up here. Now, the point is that these protocols, like USB and various forms of wireless, usually there are commercial modules available which convert from these protocols to one of the 3 that we just discussed. And for the most part, unless you are really happy writing 10,000 lines of USB driver code or cross-compiling a wireless driver stack, this is a lot easier for most people. And these modules are not too expensive these days.
Yeah, and there's details like, so for instance, the Ethernet interface, the Mac specification, that is actually not a free document. You have to spend like $1,000 to purchase a licensed copy of the Ethernet specification. Obviously, there are billions of Ethernet devices. I guarantee you that most of those engineers who implemented them didn't purchase or look at this document. And you could do the same. It's just, you're sort of getting into where like professional engineering is like this, developing this stuff constantly. Wi-Fi, I mean, how many Wi-Fis have we had in the last 6 years? You know, keeping up to date with all this stuff is tricky. And same with USB. You can now buy Atmel chips that directly support USB, but it's a much more complicated and sophisticated protocol. And that's how, you know, an Atmel chip could be in this mouse, or it could be in a laser, you know, it could be in all kinds of things. And we're not going to get into how you design, you know, USB peripherals for computers.
But what you can all do is buy a USB serial cable or USB serial chip and just stick it on your board. And that's just a chip and then like 4 capacitors. And then it talks serial, and you guys can do serial really easily with a couple of lines of code. So we highly recommend doing that, but you do have the ability to use these other interfaces which you may be familiar with.
So we're not going to stop you if you desperately want to do USB stack implementations on the next Mega, but
We aren't going to help
you're going to help you. We're not gonna-
Yeah.
Whereas if you want to talk serial to a computer, USB to serial, great.
Why would you want to directly use these? Is there any advantage to?
Yeah, so there's a number of direct advantages to using it. USB is much more common on a computer than a serial port is these days. So if you want to have a device which can plug straight into a computer and can talk to software on it, a USB serial converter is a really good way to go, because then people don't need special software. You just plug it in, and Windows, Mac, and Linux all know how to recognize the standard chips. So
Now,
that's nice.
There is sort of a cost complexity.
Yeah.
That chip is $5, and it's there because it's really convenient for $5. So their price has not changed in 5 years.
Yeah, but that's a trade-off.
And they have good driver support.
Yeah.
There are other USB serial adapters and chips that we are never going to recommend to you because they have terrible drivers.
Yep. And so for using wireless, the reason there is pretty obvious. If you want to communicate data off of your device without using a wire, you're going to have to use some sort of wireless module.
I meant like directly as opposed to
Yeah,
using.
so
this.
if
Oh,
you
using it
directly
directly,
use
okay.
USB,
Well, you can directly use all of
you're
them.
not, so code-wise, in terms of software on your computer, to talk to a USB to serial adapter, you just have to open a serial port.
Okay,
It's
so
crufty and old,
I
but
think-
direct USB HID.
Yeah, so
you can do.
the reason that you want to use one of these directly is because you want to use parts of the protocol that are not available through a conversion, or because you want to do it really, really fast, or because you want to use fewer parts. So for example, USB, like USB 3.0, I don't even know, what is it, like a gigabit or something like that? It's crazy fast,
It's
right?
just PCI Express.
Yeah, well, it's really, really fast. It's much faster than you would be able to run a serial like RS-232 or possibly even SPI. Well, probably not SPI. But the point is that if you have a direct connection to your microcontroller, you can probably push a lot more data through it. The cost is that you have to implement a USB driver, which is usually like a couple thousand lines of code to get everything sorted out. Usually you can find it online and modify it or something. Like Loofah and stuff. But
Yeah.
anyway, the point is the code is a lot more complex, but you can do fancy stuff like then you can enumerate as a keyboard, or you can enumerate as like a flash drive, right? Which you can't do with the USB serial module. That will only give you a serial port. Similarly with wireless, you can, if you're directly doing it, you can do all sorts of stuff like via router, or run a mesh network or things like that. Now modules aren't going to support that. They're just going to be like, okay, here's how you send data, and here you can set an address and like stream packets out or whatever, which is often all you really care about doing. So that's the trade-off. Is you are trading off all of the full functionality of these protocols for a small subset, and you're paying a little extra money for these modules at $5 to $10. But the upside is that it's a lot simpler to use those modules in your software and in your layout.
Yeah. So if you wanted to build a USB mass storage device, probably that's more like grad level ECE class in systems engineering. And you have, this is where like the example is the code gets worse and worse, the documentation gets worse and worse, and you're like kind of these bare metal USB stacks. Like if you have to implement a stack on your embedded system, embedded system is much more complicated.
So Brian and I recently did an Ethernet to a microprocessor, a little bit bigger than what you guys are using. How long did that take us? That was
Well, even using other people's drivers, in theory, their code should have just worked, but then rounding out those details took a couple weeks.
yeah,
Of just figuring out what was wrong with our implementation that was slightly different from their
between
implementation.
both of us, and it turned out that we were using a 3-port switch chip, and we were selecting the
We're
wrong.
talking to the wrong
We were
part.
talking to the wrong physical transceiver on it. And
So there's just this sophistication, right? Serial is really simple. It's been around since the 80s. It was state of the art in the 80s, but now it's pretty easy to wrap your head around. And everything else has gotten more and more complicated. Like USB is kind of complicated, but really because there are these standard profiles. Wi-Fi is
crazy complicated.
and every new version of Wi-Fi that gets more and more sophisticated so that you can stream, real-time video, in your bathroom, in your house from a router, it's like, it's hard to do. There's a lot of engineering that just keeps changing constantly, right? I don't even want to know what the next wireless standards are.
Yeah.
Bluetooth is the same. They keep trying to fix it so that people's phones don't keep dropping out with their,
Headsets.
because they don't care what's going on, right? No one cares. They just want it to work. And they, people will basically beat at these things until it works. And Zigbee, right? It's being rebranded so it's basically a low energy. mesh
So anyway,
network.
these protocols are nice if you want to talk to other stuff and not need people to have special hardware, and you can do it with these modules.
So rather than implement USB, you can just get an off-board USB serial adapter. Super easy. The one you would have was like $8 from your
Yep,
mini
so if you
gadget.
guys
You
look
already
at
have
the
one.
mini gadget schematic, you can see one of these on there. Or did we do it in the cable?
It's the cable.
It's in the cable. Okay, so if you look at the part for your mini gadget cable, that part actually, the cable itself includes a USB serial converter. And so the chip on the mini gadget just sort of talks TTL serial out to this cable, and in the cable it gets converted to USB.
And you can put it on your board if you want it a little prettier, because then you can plug a USB cable into your board instead of this special cable. That can be nice. And then it shows up as USB to serial adapter. But some will let you do special API driver calls and like via mouse instead. And the FTDI is generally, I'd say, the best software support. There is trickery possible using things like eUSB, where someone has basically, you can like get this and like mess with it and like on your tiny microcontroller, your USB peripheral. But it's ugly and complicated. If you want to do something else, like 80% of your processor is busy doing USB, and if you're lucky, you can sneak in your 2 or 3 sensors without breaking the USB thing. And if you break it, I'm not helping you fix it. That's why we recommend just Serial. Serial is super easy, very handy. Same with these. So these are all there. See the word serial just keeps coming up. It's like Zigbee, you can get like direct things. You can get SPI Zigbee adapters, but serial is just so much easier. So like roving networks does a lot of these embedded modules. There may be other ones. I don't work too often. Where like, you want to talk Bluetooth? Here you go. Here's the RN41.
You just stick it on your board, and then you just sort of like talk to it and be like, hey, could you send this data out for me? And it's like, no problem, I'll send it on Bluetooth for you.
And here's the like, what is this, $20 for an RN41?
It's like 14 bucks.
14. I found an $8 one on Deal Extreme, which ships straight from Hong Kong. Maybe it's as good, maybe it's not. I don't know. But when people are talking about Arduino stuff, sort of nice that right now, if you search for whatever protocol you want to talk, and you add the word Arduino, chances are somebody sells a BLA to serial adapter, and somebody has Arduino example code. So like if Arduino works with it, then you probably can get it working too. Especially with all that stuff over the place. Zigbee, I don't know that you can use it. It's cheap.
I guess the one time you use Zigbee is useful if you have a bunch of little gadgets that you want to talk to each other. Because unlike Bluetooth or Wi-Fi, Zigbee is just like an open networking protocol. So like there's no control over it. When you send out a Zigbee packet, like all the other Zigbee radios in the area just get that packet as long as they're on the same network name as you. So if you want a lot of gadgets that are talking to each other, Zigbee is a good option. Bluetooth, you need to have some sort of host device. Wi-Fi, you need some sort of router, stuff like that. Zigbee, you
It's
just
good for just mesh networks. This is actually what it was used for. Also, the range on Zigbee is great. Like, if you wanted a 1 mile range, because you're gonna have these sensors out in the fields, Zigbee has 1 mile, and you can get more than this.
It works.
It works okay.
It works. It's better than Bluetooth.
And
it's
Bluetooth is,
better
10
than
meter
Wi-Fi.
plus or minus, whatever that wall is in between you. So you can do this wireless stuff. It's not too bad. You want to look for a module. You can do whatever you want, but I strongly recommend doing a serial module. Only because, for this class, we don't want to force you to make, software stacks. It's just not worth the time. You're not trying to save $8 on a million count, by implementing it yourself. That's basically it for the miscellaneous.
So welcome to digital interfaces.
So here's just sort of the high level, get thinking about it. When you're looking for, a device that you're going to shoehorn into Gadget 2 to meet your minimum qualifications, think about what you want to do and what you want to play with. Because you're going to have to go out and find this stuff. And then next week we're going to talk about specifically how you implement this stuff. Serial is pretty easy. SPI is pretty easy. I2C is also pretty easy.
Pretty easy.
It's very straightforward. Whether or not it works for you is another question.
I think at the end of class, we'll spend the rest of the time answering questions people have about their gadget boards and stuff like that. So.
All right. Any Gadget 2 questions? All right. That's that.
No, but give me 2 seconds. I'll show me where the